Swayam Prabha. Digital India. Educated India.
So my first objective in solving this problem is, first I have to make sure that whatever is this model, see this model depends on this parameter theta d, whereas the left hand side of that quantity was depending on the parameter theta g, and there is no as such direct connection between them. So I have to make sure that these two quantities are equal. That is the first thing, okay? So that it essentially, what does it mean? It means that this guy is actually discriminating between these two types of images, and after that I have to try to modify the parameter of the data generator in such a way that this probability eventually becomes half. And that is where police is confused actually, right? So what I am saying, let me repeat. In the first step, I am trying to make sure the police does as good a job as possible in terms of differentiating between the fake currency and the genuine currency. With whatever technology these thieves are using currently to produce the fake currency, they may not be using the best technology. They want to generate the best technology, but currently they are using some technology. With whatever technology they are currently using and producing the fake currency, police should be on the top of the game to discriminate between the fake and genuine. Now tomorrow if they change their technology, they improve the technology to produce better fake currency, police has to again adapt itself. And eventually thief wants to reach to the situation where even after adapting, police finally gives up and they say that I am able to not discriminate, right? Because that will be the victory day for these thieves actually, right? I mean, this is how its theory looks like, bit, you know, in negative sense, but this is how the principle works behind this generative adversarial network actually, right? So what we do is we write something called log likelihood function actually. So there is this function, okay, those who cannot follow don't bother about this. What essentially this function measures, this functions measure if x is coming from PD or x is coming from PG. See, if x is coming from PD, then what I expect my d of x, which is the output of this function, should be 1, and if it is coming from PG, then 1 minus dx should be 1, because dx should be 0, right? It should predict accurately. If police is very smart, then if the data x is generated by PD, then police should predict it 1. If data is being generated as per PG, then police should predict it 0, which means 1 minus dx should be 1. So essentially this quantity should be, you know, as high as possible for this police to be good police, correct? And that is what we are writing here. So this function, this L theta g comma theta d, now you can connect from the first part of the story. We have a function which is of the two variable, theta g and theta d. They are like x and y in the morning actually. What is theta d? These are the parameter of this network. What is theta g? These are the parameters of this network, right? So this is like f x comma y in the morning, right? For any given technology used by thief, which means clamping the value of theta g, if you clamp the value of theta g, you want to maximize over theta d, right? You want to find that parameter value of this network such that they are the most robust classifier, okay? Now, so that is what is this equation happening. And then after having that, what you want to do? So for any given assignment of theta g, the maximizer theta d star of L satisfy the following condition. This is a simple lemma which shows that for this function, if you claim the theta g and take the maximizer theta d, that theta d will also satisfy this equation, which was one of our requirement, okay? Next is this theorem. This says now you want to minimize this, right? Because once the police has caught up, for any given value of theta g, now this phi theta g, which we saw in the previous equation, right? This phi theta g, this tells me the police capability. In some sense, this is measure of how good is police actually, right? But what you want now? You want to minimize it actually, because if you want police to be confused. See, every time you have certain technology, police is the best possible manner they try to equip themselves to discriminate, right? But you want to advance your technology so much so that even with the best effort of police, they are unable to discriminate between the true currency and fake currency. So what would be the objective of thief? The objective would be against any choice of their technology theta g, they know that police will come up with their theta d and all that, such that this will be their performance. So then they want to change their technology such that this is minimum possible gain for police actually, because police loss is their gain actually, right? So you can see that this problem becomes kind of a arg min-max problem over these two variables. And what is the beauty of this formulation? See, these expectations I am taking, this expectation functions always convexifies the problem actually. That's the interesting part, okay? So over this probability distribution, they will be convex. So then what happens is that von Neumann's theorem becomes useful, and then they have the solution actually, right? So, but still in the original paper, in the 2014 paper, they proposed an algorithm, and that algorithm was not finding the global min-max point. Instead, it was trying to find, so they did not give any convergence proof for this algorithm. They gave, but in a very simplistic setting. Let me tell you what was the algorithm. Suppose you were to solve this optimization problem, the previous optimization problem. So now what is the problem? This is the complicated looking expression, and you want to find the parameter theta g and theta d such that that is the min-max point of this function. And how do you find that min-max point? This was the algorithm proposed, okay? This is called 2-time scale algorithm. What is 2-time scale algorithm? You can look at that there are two for loop. One is outer loop and one is inner loop. For one iteration of outer loop, there are several iterations of inner loop. And these several iterations of inner loop are essentially the police is trying to catch up. So police has to be really fast in catching up. Thieves can afford to be slow, right? So this inner loop is called faster loop. Here what happens? For k steps, you generate m noisy samples, and using those noisy samples, you generate these sample images, and you also take some m real images which are given to you as your training sample, right? True images, and then you try to do a simple gradient descent algorithm on top of it, where you move in a direction of theta d. So you are modifying the parameter theta d here, right? It's like x and y, okay? So you are trying to maximize on y for a clamped value of x. Here theta g is clamped, and now you are trying to maximize on theta d, and therefore you take this gradient descent step to maximize your value. You do couple of these iterations. After that, you come out, and now you clamp the value of theta d fixed actually, right? And then you do, few iterations, not few iterations, just one iteration here, right? In order to modify the theta g, because you have to minimize in x actually. So these are called gradient steps. I don't know how many of you know the gradient descent algorithm. At given function f at x, you calculate the gradient, move in the negative direction if you want to minimize, move in the positive gradient direction if you want to maximize. So that's what we are doing here. And this inner loop is running at a much faster rate than the outer loop, right? Within one epoch of outer loop, when one revision of theta g, multiple revisions of theta d would have taken place actually, right? That's why it is called 2-time scale algorithm, and this was originally proposed in this paper, okay? So essentially it ensured that the critique is as strong as one can get for the current generator, as I was telling you, and this outer loop, what it does, it ensured that generator can fool the current critique as much as possible. That's the idea, okay? So these are some discussion points. Maybe not, I will not go into all of those details because this is maybe little bit out of the scope of this discussion. But let me just tell you a few other issues with GAN. So the problem with GAN is that there is one important problem with the GAN is mode collapse problem. What is mode collapse problem? In your original distribution, if your distribution is multimodal distribution, for example, so here is let's say in this space there are some pocket where probability mass is high, then there is another region where another probability mass, then there is a far off region, there is a probability mass, right? Then you have this multiple peaked distribution, right, where the probability mass is peaking at different places actually. Those kind of distributions are hard for GAN to pick up and learn. That's a big problem. If you have a single modal distribution, they still can manage. But if you have multimodal distribution, that was one of the problem in original GAN, and then many paper came afterwards to fix in different ways and all that, right? Another problem is called oscillation problem. So sometimes what happens is because it is more like, this is called alternating optimization problem, right? This min-max problem. You first clamp one variable, do optimization in another variable, then clamp another variable, do optimization in the previous variable. Sometimes what happens is if your function is a peculiar nature, you get into loops actually, you won't improve, right? You keep on oscillating. That's another problem with some of these algorithms, right? But important point what I want to tell you is this algorithm which I discussed and which was proposed in the original paper, this is an approximate solution of the original problem, namely min-max problem, okay? Although they gives the guarantee, convergence guarantee that it will converge to the min-max point, but for those convergence guarantee to hold, you need infinite number of sample. So this is how the theorem reads actually. Let me just tell you the theorem. Oops. Where is that? Yeah. So, so until recently there was no known proof for the convergence guarantee for alternating gradient scheme under the finite capacity. So original proof says that the convergence happen whenever the capacity of the nets as well as the training examples are sufficiently large. So in the original paper they proposed this algorithm, then somebody has to give you the guarantee that if I run this algorithm I will hit the min-max point, am I right? Because my problem was to solve min-max point. Somebody has to give me guarantee that it will output me the min-max point. So in original paper, what they said is you run this algorithm, it will give you min-max point in certain scenarios. What are those scenarios? The scenarios are when your capacity of the both red box and the green box, you have a gigantic large network, number one. Number two is your samples are also infinite in size actually. Then it will happen, but that hardly happens in practice, right? In practice, we take only finite sets of size of generator as well as discriminator. And in those cases, the output of this algorithm is very different than original formulation, min-max problem. But still it works. So that's what I was trying to tell you in the beginning of this talk. If you can invent a very good algorithm to solve this min-max optimization problem, right? That itself will be a big contribution in this area, right? Because even with this approximate algorithm which are not giving you truly min-max point, they themselves are doing so good, phenomenal job. And imagine if you have true min-max algorithm, how good that will work, right? Then of course there has been many more advancements in recent time. For example, people have shown that, you know, this GAN converges to local Nash equilibrium. So the previous algorithm which I was talking, it might not converge to min-max all the time, but it converts to something called as local Nash. We discussed in the morning what is called local Nash equilibrium, right? So they converge to local Nash because it's a alternating optimization, right, gradient. So it converts to local Nash. Okay, so maybe this is kind of one logical end to this GAN. There was another related problem called domain adaptation problem. Maybe I'll just flash the slides and I may not go too much into detail, where also you see this kind of min-max formulation, okay? What is domain adaptation problem? So the domain adaptation problem is something like this. Suppose you have these black and white images of handwritten digits actually. So typically in machine learning what happens? One of the problem in machine learning and deep learning is design of a classification system, where given an image, my machine should be able to tell whether it is digit 0, digit 1, digit 2, digit 9, or it's an image of cat or image of dog. That's a fundamental problem actually. So imagine that you have the images, and such systems are typically trained with the label data, in the sense that in the input you have bunch of data where you are given the image and you are given the label. You are given another image, then you are given the label, right? And using those data, you generate a system which are able to predict the label of any unseen image, right? So suppose you are given the label of the black and white images, which are handwritten digit, but tomorrow you get the colored images, which you don't have any label about, and you did not even train them actually. So how can you classify? That's the problem. And you have no label, let us say, for this new data set. Although they are data set related to images only, but nobody told you the label associated with those images. So the problem then becomes is, can I still use this previous model or these data sets to train a classifier which will work good even on these colored images also? So these are called domain adaptation problem, right? You have solved problem in one domain, but by taking this model, can you lift and shift that model into another domain also? And will it still work, right? So I'll not go into too many details. This itself is a vast ocean, but I'll tell you one simple interesting thing, and then that may be a good point. So there is a one setting of this domain adaptation called homogeneous setting and covariate shift assumption. So what is homogeneous setting? Suppose you have source domain where x and y both are coming from some, let's say, image and the label, right? So x is the domain of image and y is the domain of their labels. And this is same. Like for example, in that image case, the black and white and the colored images are coming from same 74 cross 74 Euclidean space, right? So x is same, right? It's just that different points, they are from different point. Colored images will be different point. Black and white image of same digit will be a different point in that same space, right? Actually. Then you assume that the joint distribution of any point, although the joint is same, but the condition, although the joint is different, but the conditional distribution is same. P of y given x is same, but the marginal distribution and the joint distributions are different. Can you see that? So I wrote that P, so any point which I sample from this domain, in source 1 is Ps x comma y, and in the target domain this is Pt x comma y, and if you split it using base formula, you get this conditional and this is called marginal, right? So the conditionals are same, the marginals are different. What does it mean? Look at this picture. Suppose this x is your data, x is this axis and y is this axis, suppose, right? Now this x, this red curve tells you the true function as in for any given value of x, what is the value of y? This is kind of a regression problem, which means it tells you P of y given x. This is the model for P of y given x. It's a deterministic model. For any given x, there is a fixed value of y. But now, these blue dots are the sample coming from some distribution Ps of x. And black dots are some x which you sampled using Pt of x. Now suppose somebody gives you these blue dots, right? And you try to fit a model, try to fit a relationship between x and y. Probably you will end up fitting this green line, correct? Now, if now somebody tells you a black point, somebody gives a x corresponding to this black point and asks you to predict what will be the value of y, and if you use this green line, you will be predicting the value of y this much, right? This is the model for x and y relationship you ended up predicting, which is a very wrong model, right? Why? Because you did not sample this region at the time of building the model. Because this region was under, the probability of this region in the source domain was very low, so this sample never showed up in your data. And therefore, if you just blindly use this model for this target domain, you will be failing miserably. Okay? So this is called the covariate shift assumption and the domain adaptation problem. The idea here is this. What you do, you take the data x from source domain and target domain, you apply some mapping f like what we discussed there. So take this x, pass them through some function such that this induced distribution in this space, this we call as a latent space or Z space, the induced distribution is identical. Whether the data is sampled from blue dots or the black dots, I apply some transformation on the blue dots and the black dots such that if I look at the probability distribution in the transformed space, then blue distribution and the black distributions looks identical. Then you cannot discriminate whether the data point is coming from blue or black, right? But how do you do that? And that is where there was one very influential paper. Maybe I'll just stop after that. So this is called a adversarial domain adaptation problem. This was proposed, this is ICML 2015 paper by Gannon, and very important paper, very popular paper. So here what they do is, suppose you have an image, right? Like I told you that you have black and white and the colored image. And you have the labeled example only for the black and white. You don't know for the colored image, but you want to train a classifier for the colored image also. What you do? You pass an image through this green pipeline. This green pipeline is nothing but some gigantic neural network. It will transform this image into some kind of feature vector, f. Okay? This feature vector is called latent feature vector. Now, there are two pipelines from here, this blue pipeline and the red pipeline. These two are also neural network. So if the image is coming from the source domain where you know the label, then what you do? You funnel it through the blue pipeline and compute the loss, this log likelihood function, and you pass the loss back through the gradient propagation and you update the weights. But if it is coming from, let's say, different domain, the two different domain, then what you will do, you will assign those virtual labels like what we talked about in GAN actually. You assign the virtual label to the red image, black and white image as 1, virtual label to the colored image as 0, that becomes a different kind of label, that is called domain label. And then this is a separate classifier which you train it using again the same feature vector f. This is called domain discriminator actually. Okay. Now if you train this entire machinery, then hope is that that problem will get fixed actually. That diagram I was showing you, right? This diagram, you will not face this problem. This green line will get pushed somewhat this actually. Okay, that's the hope. And in order to make this domain discrimination, you want to learn the feature vector where nobody can distinguish whether it is a colored image or a black image. And precisely that formulation, if you write it down, very similar formulation, here the problem becomes a saddle point problem, not a min-max problem. Okay, this just missed actually. Sorry, this computer is a bit slow. Yeah, so this is a horribly looking expression probably on the face of it, although it's very simple and I don't want to get into right now. But essentially what happens, each of these blue, red and green network have their own respective parameter which are denoted by theta f, theta y and theta d. So this is a function in 3 variable, not just x, y, z, not just x and y, it is x, y and z, think of it this way. And in these two, jointly in these two things you want to minimize and this dimension you want to maximize at the same time. But it is not a min-max problem, it is a saddle point problem. Why? Because these minimizer I am clamping in maximizing and the maximizer of this I am clamping in minimizing. Okay, and that is the formulation of this adversarial domain adaptation problem. This happens to be a saddle point problem. Okay, so this is essentially the problem which we discussed in the morning. So in order to solve this problem, you have to solve the saddle point problem. And again, there is no prescribed algorithm. This paper also proposed a very similar algorithm like what we saw in the GAN, this alternating optimization scheme, where you clamp one x fixed, maximize in y, clamp that y fixed, minimize in x, keep doing back and forth actually, right? And all of these schemes gives you local saddle points actually. They don't give you neither min-max nor the global saddle point, but they themselves work best. And the good part is these algorithms are very efficient, right? So if you want to get more into this area, you can read about them. How can you improve this algorithm from here onwards and get better algorithms actually, right? That's what my objective of this entire talk was. So finally where we are, this is probably my last slide. So we talked about 2 problems, right, today. I mean, one was this GAN and one was this domain adaptation. And we talked in the morning 3 concepts, right? One was min-max or max-min, doesn't matter. Another was global saddle point, one was local saddle points, right? So this, actually this is wrong, this is not domain adaptation, this is GAN, okay? This is domain adaptation problem. So in the GAN problem, the underlying problem formulation happens to be a min-max problem. But the algorithm which was suggested actually finds its local saddle point, not the min-max. On the other hand, this domain adaptation problem, the underlying formulation asks you to find the global saddle point, which is a very hard problem, but the algorithm which are typically given in the papers without much guarantee, they still find local saddle point. Because in the morning we saw, right, local saddle point is the most easiest things to do. Keep doing alternating gradients actually. So my point to you is that there are several of problems, several application areas in deep learning and machine learning where the underlying optimization problem nature is that either you need to find min-max points or you need to find the saddle points, which is equivalent to 2-player zero-sum game problem. But then because of the lack of the efficient algorithms, and genuinely they are hard problem actually, you end up finding the local saddle points, right? So if any of you are interested and excited about some of these areas, this is one area to undertake as a research topic, that can you invent the better schemes or better algorithm for some specific problems where rather than just getting the local saddle point, you get either the min-max point or you get the global saddle point, or if not absolutely accurately, reach closer to them, or give some theoretical guarantee. At least tell me that, okay, even though I am giving you the local saddle point as the output, but how bad or good it is with respect to the min-max point. Okay, although you wanted me to give you min-max point and I am giving you local saddle point, I am not giving you what you demanded for, but can you tell me how far I am from? That also will be a good value addition actually, right? So these are the some of the application I thought I had in my mind, because they are very contemporary actually. You can see that, and they are on top of AI and this machine learning and deep learning and all of them, and they have this kind of signature characteristics of having this min-max formulation, game formulation. So it's like a common area, and you can take up this as an interesting topic. Okay, maybe then this is a good point to stop. Maybe, and if any question we can take, right? We are breaking little early though. Okay. Unless you have any more question, maybe we'll just stop here. Okay. Yeah, so this I guess pretty much I covered everything. All right.